So this is the FedEx problem. This is joint work with Amos Fiat, as well as Anna Karlin and Elias Koutsoupias. OK, so what's the setting I'm talking about? The FedEx setting is where we have a single customer. I'm going to stand over here. OK. And the customer has a package they want to ship, and they have a value for that package of how much it's worth to them to have their package shipped. And she also has a deadline when she wants it received by. And if she gets the package received by her deadline, it's worth her value V to her. If it's received after her deadline, it's not worth anything to her. So you're trying to ship something and you have a deadline. So as I said, you're indifferent if it's shipped early. All you care is that your package is received by your deadline. And these pairs of value and deadline are drawn from some joint distribution F. We're in the Bayesian setting. And we're talking about FedEx here. You're FedEx. You're trying to decide what's the optimal way to maximize your revenue from customers who have a value and a deadline when you can sell a discrete set of shipping options like one-day shipping, two-day shipping, and so on, as FedEx does sell, such that you maximize your revenue. And we're in either the single bidder setting or the unlimited supply setting, however you want to think about it. We'll talk about it as single bidder. OK, is the setting clear? OK. So we're calling this the FedEx problem, but I want to note that it's more broadly applicable outside of just FedEx. For example, it was originally inspired by Bitcoin, where you have a bunch of customers who are trying to submit their transaction fees so that their transactions get processed by their deadline, and there are different blocks, so they have different deadlines for blocks. Or you can think of it as when you're trying to buy an internet plan, and maybe you have a certain speed of internet that you want. You want at least that speed. This is like your level of service requirement, and if you get above that speed, you're happy, and if you get below that speed, it doesn't satisfy you. Or maybe you're buying a car, and there's like the base model and the various upgrades, and you want to make sure that you have a GPS or a backup camera or some other feature, and so you're happy if you buy a model that contains that feature or any more fancy model. So this is any setting where the customer has a required level of service or time sensitivity, and they need to get at least that level of service to be happy. OK. So what are the assumptions in the setting? As I said, we're in the Bayesian setting. So there is a cumulative distribution of these value deadline pairs. And we can break them down into the marginal distributions. So Fi is the marginal distribution for anyone with a deadline I. If you need your package within 2 days, then Fi is the distribution of values for people who want their package in 2 days. And Qi is just the probability that you get someone who has a deadline of day I. So Q2 is the probability that you get someone who wants their package in 2 days. Our only assumption is that Fi is atomless and strictly increasing, just to have everything be nice and continuous. And for this talk, we'll talk about things in some range 0 to h for any h, which is the upper bound on the support of the distribution, but you can also extend it to be 0 to infinity. OK, so what is this? This is a revenue curve. And let's just first talk about the simplest thing that most of us already know. What happens if everybody just wants one-day shipping? What is this object here? It maps price to expected revenue for posting that price. So this is just the price times the probability that the customer is willing to buy at that price. And so what's the best thing you can do if this is your revenue curve? How should you maximize your revenue if everybody just wants one-day shipping? You should just post the peak that gets you the most revenue. This is Meyerson. We all know this. OK. But everybody needs to understand what a revenue curve is for the rest of the talk. So let's make sure we understand this. OK, good. So now what do we do if we have 2 different days? So what is this revenue curve? This is everybody. When I say day 1, I mean people with a deadline of day 1. They want their package tomorrow. And this is everybody with a deadline of day 2. They're willing to get their package tomorrow or the next day, either day. OK, so we're separating out the marginal distributions for people who want their package tomorrow and people who want their package within 2 days. And these are the revenue curves for each marginal distribution. So if we're selling 2 different days of shipping, 1-day shipping and 2-day shipping, what should we do to maximize our revenue in this case? Well, the easy thing to do is just to post the peaks. These are the best prices individually. We know how to solve the single 1-day shipping problem. And in this case, this is the optimal thing to do. So when the reserve prices are decreasing, it's simple. You just post the decreasing reserve prices. OK? So why aren't we done? Well, what if you had distributions that look more like this? And you just try and do exactly that. You post the best prices. Now, what's the problem? The problem is that the price for 1-day shipping is cheaper than the price for 2-day shipping. And so the problem here is that we wouldn't actually get this revenue. If you want your package in 2 days, you're just going to buy 1-day shipping. So we're not correctly reasoning about the revenue that we're going to get. So you may think this is silly. Why wouldn't the reserve prices just be decreasing? We don't want to make such a strong assumption. We don't want to assume that the marginal distributions are stochastically dominated for higher deadlines. And moreover, I can give you a silly example as to why they may not be positively correlated. For example, suppose your friend's birthday is tomorrow and you want to send them a gift for their birthday. Maybe you'll order something off Amazon or whatever. If one-day shipping is exorbitantly expensive, like more expensive than the gift you were going to buy, you're not going to do the one-day shipping. You'll be like, whatever, I'll do something else for their birthday. But if you're a surgeon and you're performing open heart surgery in 3 weeks and you need your surgical equipment there by the time you perform your surgery and it's a matter of life or death, maybe you're willing to pay a little bit more for shipping to get the equipment there. So here's just like a silly example of why they may not be correlated. In fact, in the second example, since it's a matter of life and death, maybe you would take the time to plan ahead to make sure it will actually be there in time. Okay? So I'm just trying to motivate this example of why maybe the distributions won't be stochastically dominated, why the reserve prices won't be decreasing. Yeah?
So going back, you seem to claim a result, basically, without putting it up, which was that if I solve the optimal prices for 1 and 2 day shipping, and it so happens that they're increasing, posting those 2 prices turns out to be optimal.
Yes.
Did I understand correctly?
Yes, that's correct, yes. Okay. Good. So, and the problem with this setting was that if we just post the peaks, we're not actually getting this revenue because it's not incentive compatible. So we're not actually getting this point plus this point. Okay, so what can we do instead? We can require incentive compatibility by the revelation principle. Okay, so I'm just trying to set up the problem we're trying to solve here, which is we want to maximize our revenue from, again, when I say day one, I mean customers with a deadline of day one and so on. We want to maximize our revenue from customers with each different deadline, subject to, we want bidders to report their true value and their true deadline. So these are incentive compatibility constraints. And of course, we want our allocation rule to be feasible, to be a probability in 0 to 1 of service. Okay, is the problem clear?
So you're not going to set prices, the mechanism?
It's a mechanism, so it's going to be, because it's a single bidder problem, it's going to be some sort of randomized pricing. Yeah. And the question is it randomized? What does it look like? Yes. Okay. Other questions? Okay. Okay, so as we just heard from Noam, finding the optimal auction is an incredibly complicated thing. It can look like infinite menu complexity. There are all sorts of complications in finding the optimal mechanism. So the first thing I have on this list is not actually multidimensional. This is just Meyerson, completely resolved in 1981. Everything else on this list is not a complete list, but I think it's pretty close of what we know about optimal auctions. So we have some results for you could solve a linear program in polynomial time for finite type spaces, but it doesn't give an exact characterization. Then we have a list of things here that are very, very specific settings for very specific distributions. For example, 2-parameter, uniform 0-1, single crossing, 2-item settings, 6-item uniform. And we have optimal auctions for these extremely specific distributional assumptions. The second set is a bunch of results that says, under these distributional assumptions in these settings, we know that this specific mechanism happens to be optimal. So the first set is in these settings, we know the full characterization, and the other set is we like this mechanism, here's when it's optimal. Or here are some cases when it's optimal. So this is a list of optimal auction results for the multi-parameter setting. And then there's an extremely long line of approximation results for the multi-parameter setting. And all of the results are extremely clever, but the point is that we still don't know that much about optimal auctions. And they're very complicated. And our problem is also multidimensional, partially because you can view it as this dual parameter problem where you have a value and a deadline, but also you can view it as a special case of correlated unit demand where your value for the first D services is V and then it's 0. And so our problem is one of the simplest possible multi-parameter problems, but it is definitely a bona fide multi-parameter problem. So what do? We find the optimal auction mechanism or randomized pricing for the unlimited supply or single bidder setting for the FedEx problem without any distributional assumptions on F aside from that it's nice and continuous. No regularity, nothing else. So what does this look like? Each day has a randomized price. The customer will, knowing the distributions of the randomized pricings, choose a shipping option I. Then the randomized price for the shipping option I will be drawn, and then the customer will decide whether to buy or not. So it is ex post IR. Okay, this is not a specific description. This is a very vague description of the mechanism, and I'm going to tell you in more detail how we find it and what it looks like. But here is very high level. The point is that we have this FedEx setting. It's extremely simple but multi-parameter, and what we do is we find the optimal single bidder mechanism. Yeah?
Do you know what happens if you're restricted to a deterministic mechanism?
Not really, but sort of. Let me get to that at the end. Okay, that's not what I'm going to talk about today, but let me get to that at the end. Okay. Okay, so let's review what we need for incentive compatibility. So we know from the single dimensional setting that payment is explicitly determined by the allocation rule. Here I have an allocation rule that says if your bid's below P lower, you get nothing. If it's between P lower and P upper, you get service with probability 1/3. And if it's above P upper, you definitely get served. And we know from the single dimensional setting that your payment is just the area to the left of the curve. So if your bid is P, then your payment is just 1/3 P lower, the area to the left of the curve. Also, your utility is just your allocated value minus payment, where if you bid P and you get served with probability 1/3, your allocated value is 1/3 P for an incentive compatible mechanism. So your bid is your value. Subtracting off payment, that just means that utility is area under the curve. Hopefully this is a refresher. Okay. Takeaway is that from single dimensional theory, we know that your payment and utility are explicitly determined by the allocation rule. Okay, so what are constraints for incentive compatibility? They're the two things I just mentioned, that payment and utility are determined, and also that we need our allocation rule to be monotone weakly increasing. Okay, the other thing we need to incentivize is for bidders to report their true deadline over any other deadline. For example, we want day 2 bidders to buy 2-day shipping instead of 1-day shipping, or report 2 days instead of 1 day. So because we can, without loss of generality, serve a customer who reports that their deadline is day 2 on day 2, make sure their package arrives on day 2, just delay shipping, then you would never want to bid a later day because you might not get served. So without loss of generality, all we have to do is incentivize people from bidding an earlier deadline. And so what we can just say is that you should want to report your true deadline over 1 day earlier, and transitively, you won't want to report any earlier deadline. Does that make sense? Okay, so how do we do that? You should get more utility for reporting your true deadline than 1 day earlier, and then nobody will want to misreport their deadlines. How do we say you get more utility for that? At every point, there should be more area under the day 2 curve than under the day 1 curve. At every possible bid, you should get more utility, and since utility is area under the curve, there should be more area under the day 2 curve than under the day 1 curve. So here's an example. Here we have a price of P1 for day 1, and it's higher than the price for day 2, which is P2. And of course, there's more area under the pink curve at every point than under the green curve. So a cheaper price on day 2 satisfies our utility constraint. However, if we were to switch them and have a more expensive price on day 2, of course, there's less area under the pink curve than under the green curve, so we're violating our utility constraint. I know you guys know what area under the curve is, but this is just to explain it in terms of the utility constraint. Does that make sense? Okay. So one other thing I want to mention, which may also be a review, is that we can talk about an allocation rule in terms of the revenue curve. So for any allocation rule, which is monotone weakly increasing, we can talk about it as a convex combination of prices. So for example, this arbitrary allocation rule can be broken down into a convex combination of prices. This allocation rule is exactly equal to 1/3 posting a price of P lower and 2/3 posting a price of P upper, which hopefully you can verify that this indeed is the sum of these two. Okay. So for any allocation rule, we can break it down into a convex combination of prices, and any convex combination of prices is a monotone weakly increasing allocation rule. So what does this mean? This means we can look at our revenue curve, and this is our revenue curve, the black line here, but we can achieve the revenue of any point on this blue curve, which is the ironed curve. And so here I'm just saying that 1/3 P lower plus 2/3 P upper equals P. So P is our expected price when we randomize over P lower and P upper in these proportions. Okay? And so what that means is that by randomizing over P lower and P upper with these proportions, you're achieving this revenue at P instead of the revenue of just posting P. And what does this come from? This comes from wonky irregular distributions. One other thing I want to mention is that we are in value space. So if you're used to ironing and achieving the ironed revenue curve, we're in value space, and you'll see why in a minute. Okay, we're not in quantile space. Okay, any questions about that? Okay, So the point is just that we can use randomization to achieve points on this ironed revenue curve, which is the lower concave upper bound on this revenue curve. Okay, so one more example of the utility constraint is that here, remember, P is the expected price of randomizing over P lower and P upper. This is just the expectation of the price. So if you're posting the expected price on day 1, P, and you're randomizing over P lower and P upper, but posting the same expected price, the price in expectation, on day 2, you do have more area under the day 2 curve than under the day 1 curve at every point. So this is incentive compatible by our utility constraint. But if you were to swap them, same expected price, but you're randomizing on day 1 instead of day 2. So posted price on day 2, randomization on day 1. Now you're violating this area under the curve constraint. Now there's more area under the green curve than under the pink curve, so this is not incentive compatible. And so why? Because imagine P lower is $3 and P upper is $6 and P is $5. Then if you're randomizing over $3 and $6 on day 1 and a bidder shows up, they have a day 2 deadline and their value is $4, they have no chance of wanting to buy $5 on day 2, but they'll go for the randomization on day 1 in the chance that 3 comes up and they get to buy shipping for $3. So here's why it's not incentive compatible. Okay. So the point here is that there's some asymmetry. It's okay to randomize on day 2 when you're posting a price on day 1, but it's not okay to randomize on day 1 when you're posting a price on day 2. So you need to be careful about randomization and the asymmetry between the earlier and later days. Okay, so let's discuss like a quick naive approach of how you might start trying to solve this problem. One thing you might do is you might just say, okay, what if we just optimize them together and try and set a single price for both days? So you do this, and sometimes this is optimal, but sometimes it's not. Sometimes you can further optimize day 2 and say, okay, I'm setting this price on day 1. Now I know that I can set a cheaper price on day 2 with no problem and make more revenue, and sometimes this is optimal, but in this case it's not, because we also know that you can use the ironed revenue curve, and so you say I need to set a cheaper price on day 2, but what I can do is randomize over these 2 peaks to set this expected price, and this happens to satisfy our incentive compatibility constraints, so you can actually get more revenue in this case. So sometimes this is optimal, and sometimes it's not. Sometimes you can set a price on day 2, like the best price, and then further optimize day 1 and set a more expensive price, and sometimes this is optimal. The point is that if you try and approach this from a naive perspective, it looks like a really messy case analysis depending on the distributions. Okay. So what do we do instead? Well, here's the problem we're trying to solve again. And as you may notice, it sort of looks like a linear program written in English, and that's because we formulated it as a linear program. So we formulated it as a linear program where this objective is just expected revenue using the payment identity. This is like the normal Meyerson virtual value. This is the probability of having a bidder with deadline I and value V. And then we have our constraints, which are just the constraints we've already talked about. This is the utility area under the curve constraint that says I should report my true deadline. These are the feasibility constraints that say that the allocation should be a probability, and here's our monotone weekly increasing constraint. So this is just the primal LP. It's continuous and it's infinite, but we can still write it down as a primal, and we can set up dual variables and take the dual. Don't stare too hard. It's just lines of math, basically. But the point is that you can take the dual and you can come up with, and it corresponds back to the primal, and you can come up with a list of complementary slackness conditions that say, if I find variables that are feasible for the primal and feasible for the dual and satisfy all of these conditions for optimality, then I know that my variables are optimal, and then I know that these variables corresponding to the primal describe the optimal mechanism. Okay, so that's the approach, is formulate it as a linear program, and instead of solving the linear program, use the constraints from duality to figure out what this looks like. Okay. So now I'm going to talk more about what the solution looks like and less about the technique, and at the end I'll tell you some takeaways so that we don't get too technical. Okay. So what does the solution look like for just 2 days? So let's reason about the revenue we can get from just day 2 when we post a price on day 1. So say this is the price we set on day 1, and this is day 2's revenue curve. We know, so we could just set a cheaper price here, but we also know we can iron it, and so we can actually achieve this point on the ironed revenue curve. So the best thing to do in this case is to choose the highest point to the left, cheaper than the day 1 price on the ironed revenue curve. So the best thing to do in this case, and I'm not explaining why, is just to achieve this point on the iron revenue curve by randomizing over these two peaks. This is the best thing to do in day 2. And because we can reason about this, we can formulate a curve that says, what is the best revenue from day 2 as a function of the price we set on day 1? That's what this curve is. So here it says, if we post a price on day 1 that's up here, the best thing we can do is post the reserve price for day 2 because it's cheaper, so we're allowed to do that. Which means we can get the revenue of setting the reserve price on day 2 for any price on day 1 that's more than this. So again, this is a function of the price on day 1. We're getting the expected revenue that we can get from day 2, given that that price is set on day 1. Okay, so up here we can get the revenue from the reserve price. Down here, we're getting exactly the revenue at this point by randomizing over these peaks. So it's the same as the iron revenue curve, and this is because of concavity of the iron revenue curve. So here you might notice this is why we're in value space. This is why we're ironing in value space, is because this constraint about area under the curve is in value space between day 1 and day 2. So this is why we're ironing in value space instead of quantile space. Okay, so now what can you do? We have a function here that is the revenue we can get from day 2 as a function of the price on day 1. The day 1 revenue curve is by definition the revenue we can get from day 1 as a function of day 1. So we add them together, and now we have the combined revenue from both days as a function of the price we set on day 1. So what should we do? We should optimize this and set that price for day 1. This combined green curve here is exactly what revenue can we get from both days for setting a price on day 1. So you can think of this as like a dynamic program of the revenue we can get from all of the days for setting a price on day 1. Okay, so what's the allocation rule? You set that price for day 1, and then you look at the revenue curve, and if it so happens that the best day 2 price, the reserve price, is cheaper, you set that. And if it's the case that it's ironed there, then you randomize over the 2 peaks, and you do that. So you basically do exactly what that combined curve implies that you should do, that it's giving you that revenue. Okay. This is the n equals 2 solution, and it generalizes. So we talked about this combined curve for days 1 and 2. Instead, you can start at the end and say, if I'm offering shipping options 1 through n, this is what I'm going to do for the revenue for customers who want their package in n days. This is the revenue I can get for posting a price on day n-1. And then I can add on the n-1 revenue curve, and then I can iron it and flatline it to talk about the revenue I can get for posting a price on day n-2 from the last 3 days combined. And so what you can do is you can build up the curve for all of the last days. So for day I, we can reason about the revenue we're getting from days I plus 1 through n. So there's this nice inductive solution. And then what do? Say you have your convex combination of prices for day I minus 1. If we look at just what is the jth price that's offered in this convex combination, say the jth price is Vj on day I minus 1, then we can look at the revenue curve for days I through n. This is the combined revenue curve here that we just talked about building up. And you can say what's the best price to the left of Vj, which is the jth price being offered on day I minus 1. If it's ironed, we randomize over the 2 peaks there. And we offer these 2 prices in lieu of that 1 price on day I. And this is with the coefficient from the jth price on day I minus 1. So the point is that you're getting a convex combination of prices on each day. You're getting at most 2 prices on day I for every price you had on day I minus 1, which means there's at most 2 to the I minus 1 prices on day I. Okay, and the point is, this wall of math is to tell you that how did we solve this? We solved this by looking at the primal and the dual and the complementary slackness conditions and coming up with the optimal auction. This combined revenue curve came out of the dual solution. This is what the dual variables look like. It's in terms of this combined revenue curve. And so the point is that duality is really useful for coming up with an optimal auction. Okay. So what I've been talking about is having this optimal and clean algorithm for the general FedEx problem that doesn't have any distributional constraints. We can always describe what the optimal thing to do is without case analysis. And it has this nice inductive structure, as I described, that lets us generalize to selling and shipping options. Okay, and so this is what I've mostly been talking about, and now I'm going to tell you about some takeaways from the approach, which I didn't go into detail because it's somewhat technical. So as I said, duality is really useful, not just for proving optimality, but also for coming up with what the optimal thing to do is. And this is coming out more and more now in all of these optimal and approximation results recently. We also see that randomization is important for the optimal mechanism, even with only one bidder, which is not the case in the single-dimensional setting. We need randomization here, even for incentive compatibility among the different deadlines for a single bidder. And as I mentioned, we have no regularity assumptions. Okay, other things I want to mention is that one thing you can do is take this sort of approach for other similarly very structured problems. So there is a follow-up result. Oh, so we're currently working on the multi-unit pricing problem, which was introduced by Goldner and Hagpana and Somas, which is like a very nice, simply structured problem. Why does the FedEx problem work? Because these like value and deadline constraints are nearly orthogonal. So if you find these like well-structured, simple problems, we can start to use this duality approach to understand them. So this is ongoing. You can also use the dual solution. So it's really hard to come up with optimal dual variables. And since we have these optimal dual variables, we have a canonical dual that gives us this algorithm for coming up with the optimal auction in every setting. You can sort of use this to bootstrap for other problems that are also well structured. So Nikhil Devner and Matt Weinberg have a very recent result about a nice simple budgets question where they sort of bootstrap with our dual variables and extend it to find the optimal mechanism in this setting. And by combining this approach and these variables with some of the other duality frameworks, we can get a new understanding of how ironing should work in the multidimensional setting and what virtual values should look like. And this is part of ongoing work with Nikhil Devner and Anna Carlin. So mostly I've talked about what does the optimal mechanism look like, but I also really want you to take away that we use duality to get it. We come up with this canonical dual that gives you the algorithm for finding the optimal mechanism. And even though it's not obvious, like it is if you do duality with Meyerson, it still is always optimal, and it lets you, and it's a difficult thing to come up with, so it lets us bootstrap for all these other multidimensional problems to try and understand them better. Okay, so let me mention some open problems. So as Michal mentioned at the beginning, what is the worst case gap between revenue for the optimal mechanism and just a deterministic pricing? So of course this is at worst n because you could just pick a single shipping option to sell and get a factor of n. We are working on it. Currently there's an undergrad working on it with us who has something for like 2 or 3 days. And we know that using the same procedure with a slightly different type of ironing, you could get a characterization for the optimal deterministic thing, but it's unclear what the gap between deterministic and randomization is at this point, so this is still open. What is the worst case complexity from the randomization? So I mentioned that at worst it's to the I-1 prices on day I, but we didn't look into this at all, so that's a good question. And also other models for utility and factoring in costs for the FedEx problem. Yeah, so thank you. Yeah.
I'm trying to imagine what would this specialize to for regular distributions?
What does this do for, so for regular distributions, as this multi-unit pricing paper calls it, so price regular meaning regular in price space or in value space. So since we're doing our ironing in value space, if it's regular in value space, if it's concave in value space, then all of your combined curves will be concave and there will be no randomization. So we know that under this type of regularity that everything is deterministic, but this is not standard regularity because it's regularity of the curve in value space, which has this distribution multiplied by it. So it's like times fi of v. Yeah, so under this weird type of regularity, everything's deterministic. Under standard regularity, it's different because once you multiply by the distribution, it may no longer be monotone. Yeah, good question. Yeah.
So what you call ironing in value space here is what I think is in the economics literature called complexification. You look at papers from like 10, 20, right? It's the same.
I'm not 100% familiar with the economics literature, but you're taking the concave closure of the curve,
No,
which is a common thing, yes.
I think that's specifically the relevant literature from like 20 years ago, whatever, by the reference group calls something very similar. They don't look at this problem.
Yeah.
What you call ironing in value space,
Yes.
they call complexification. So
Sure.
in terms of terminology, depending on
And in terms of the duality, it makes perfect sense because we're even dealing with the negative revenue curve actually, and you're just convexifying it exactly. But the analog to like the Meyerson stuff is ironing. So yeah, exactly. Yeah, Chris.
So you have like if suppose my deadline is in 4 days,
Mm-hmm.
and can I just like always try set the 2 days and then see what the randomized price is, and then wait 1 day and do
So the mechanism is just a one-shot mechanism, right? You're a single bidder at the beginning. You say, "Here's my deadline." You only know the distributions of the prices. You know the probability that any price will be drawn for any deadline. You could say that I want my package in 2 days, and then the price for 2-day shipping will be drawn. But you can't suddenly be like, "Oh, now I want 4-day shipping." You can't change your mind after. It's like you have to commit to the deadline. And knowing the distribution of the randomized prices, because it's incentive compatible, you will report your true deadline. Yeah. But a dynamic question is definitely interesting, although it's not what we talk about.